Okay, so in this video, I'm going to talk about Chapter 9, which is on nonlinear differential equations. Okay, so in Chapter 7, we covered linear systems of differential equations. Okay, so here we're going to generalize that idea and look at nonlinear systems. So we have two dependent variables, x and y, that are both functions of t. And so we have the x dt given as some function of x and y, and dy dt as some function of x and y. Okay, so in Chapter 7, those functions f and g were both linear in x and y. Now we're generalizing so that they are nonlinear. So I have an example here written up on the board. What happens is that the analysis of a nonlinear system relies heavily on knowing linear systems. Okay, so the first thing that we do with a nonlinear system is we find what are called critical points. And so critical points are basically these constant solutions. Okay, so if you think about it, a constant solution, or if x is constant and y is also constant, then the derivatives with respect to t are both zero. Okay? So we can find these constant solutions by setting the x dt and the y dt both equal to zero, and then solving that nonlinear algebraic system. Okay, so let's do that for this system. Okay, and keep in mind that when we do try to find critical points, we're solving nonlinear algebraic equations, which we really have no set method on solving them. We just kind of use some common sense. Okay, so for this system, if I set both of these equations equal to zero, it's easier to work with the second equation. Okay, because from the second equation, we can see that either x is 0 or y is -2. Okay, so let me just first write down that the critical points for this system are, well, if x is 0, and we can pretty much do this in our head. You'll see that. So if x is 0, I can plug that into the first equation, okay? And if x is 0, I'm left with, so I guess let me write over here, x is 0, what happens in the first equation? In that first equation, and this minus sign I can wipe away if I'm setting it equal to 0. I can get rid of that. So if x is 0, I have minus y, and then 1 minus y. And that, of course, is set equal to 0 as well. And so here I basically solve for y. So either y is 0, so that would be one solution, or y can be 1. So if x is 0, y can be either 0 or 1, and I have two critical points from setting x equal to 0. And now if I look at that second equation, if I consider when y is -2, okay, I can plug y equals -2 into the first equation, and that leads to x plus 2. And then, let's see, 1 plus 2 is 3, and 3 minus x. And that gets set equal to 0. So if y is -2, then x is either -2 or 3. So these are the four critical points, okay? And it turns out that we can basically analyze this nonlinear system really close to those critical points using what we learned about linear systems in Chapter 7, okay? And so that analysis relies on computing something called the Jacobian. And what the Jacobian is, it's basically a matrix of derivatives. And so I'll talk about that now. So if this is the nonlinear system, the Jacobian matrix associated with this nonlinear system is this matrix we're calling J. It's a function of x and y, and it is a 2x2 matrix that is df, dx, df, dy in the first row, okay? And in the second row, dg dx and dg dy. Okay. So you see that in the first row, we take f and we differentiate first with respect to x and then with respect to y. And in the second row, we take g and differentiate with respect to x and then differentiate with respect to y. And these are the first partial derivatives for f and for g. Okay. So as an example, so I'm going to write down an easier example to deal with than the previous example. So consider dx dt equal to 4 minus 2y, and dy dt equal to 12 minus 3x squared. Right? So this is a nonlinear system. We can solve for the critical points. So the critical points are, so here we can just set the first equation equal to 0, and we see that y must be 2, okay? And if y is 2, well, that doesn't really mean anything for the second equation, but if we solve the second equation, we get that x is either plus or minus 2. Okay, so that leads to 2 critical points. So the critical points are minus 2 and 2, and also 2 and 2, right? And so what we're going to do is we are going to look closely at one of these critical points, and to do that, the analysis of of the linear system is going to be useful. Okay, so to do this analysis, we compute the Jacobian for this system. So the Jacobian is, right, so df dx, if we take our f and differentiate with respect to x, of course we get 0, right? And then if we differentiate this with respect to y, we get minus 2. Right? And then if we take the g and differentiate with respect to x, we get minus 6x. And then if we differentiate with respect to y, we get 0. Okay? So what we're going to do now is we are going to look at one of these critical points. And the critical point that I want to look at is 2, 2. So let's look at critical point 2, 2. So to do that, we're going to evaluate the Jacobian at 2, 2. All right? So let's evaluate the Jacobian at 2, 2. And if we evaluate at 2, 2, all right, there's only one place to plug in one of these variables, and that's here, of course. So if x is 2, we get a minus 12 in this spot here. Okay, the others are all constant. Okay, so this is the matrix that we get. And so what is important about this matrix? Well, it turns out that if we zoom in on the point 2, 2 in the phase plane, okay, that the phase plane near 2, 2 looks a lot like the linear system x dot equals ax. This is a. Okay. So let's take a look at that system x dot equals ax, where this is a. We're considering x dot equal to the system that looks like this. Okay, and so now I'm using the vector x to represent both x and y. All right, well, to analyze this linear system, we find the eigenvalues. So those eigenvalues are given by, it's pretty easy to see that the characteristic equation is lambda squared minus 20 to the 4th set equal to 0. Okay. And then, of course, this leads to eigenvalues that are equal to plus and minus the square root of 24, which simplified is 2 root 6. Okay. And so here we have real distinct roots that, where one is positive and one is negative. So this would lead to a saddle point. So it turns out that for our nonlinear system, we look near the point 2, 2, it's going to look like a saddle point. Okay. And as far as more details about that saddle point, we can look at the eigenvectors that correspond to these eigenvalues. And so if I look at lambda 1, so let's say lambda 1 is equal to minus 2 root 6. You can compute on your own that v1 is equal to 1 over root 6. Okay. And if we were to look at lambda 2, which is 2 root 6, let's see, we end up getting an eigenvector that I believe looks like minus 1 root 6. In any case, if you really want to see a picture of what the phase plane looks like near 2, 2, we can always use p-plane. Okay, but what you'll see is that if you zoom in on the point 2, 2, you'll see a saddle point. Okay, and you'll see trajectories that sort of mimic the eigenvectors that we have here. Okay, and so I'll say that you can actually see. You can either use p-plane or you can actually look at figure 9.2.8 in the book, so it actually shows a phase plane for the system.